Welcome to Ask and Learn.
In example 3, we graph the function x squared times x plus 1 cubed all over x minus 2 squared times x minus 4 to the fourth power just by doing a rough sketch of it and then using that rough sketch idea to look at certain pieces of our graph. So we can zoom in or zoom out to kind of look at particular overarching structure of the graph to find our minimum values. And we find that at about x is equal to negative 20, x is equal to negative 0.3, and 2.5, we have minimum values. So what we want to do is to use some kind of cast system to find the first and second derivatives. We want to use the graph of the first derivative to confirm that those minimum values we found are all of the given minimums, and we didn't miss anything. And also, we want to use the second derivatives graph to estimate our intervals of concavity as well as any inflection points. So you might see from what f prime is, what they say in example 3 about trying to take the derivative of f is going to be way too time consuming. I mean, that is pretty big and bulky, so I can only imagine the algebra we had to do to simplify it to that point. So just go ahead and plug in f of x into your favorite derivative calculator, and you should get the same thing that I have here on the board. Now, this first graph is just an overall graph of what it looks like for f prime, but it doesn't really give us much information. So this second graph over here is when I went in and zoomed to the left of the graph, and I made sure to go all the way out to at least negative 20 to get these other values. So let's just start from the left. So it does look like about negative 20. We will have a minimum because we're decreasing since the function is negative to the left of that point, and then increasing after, which tells us we have a minimum there. Then, so over at x is equal to 1, so let me put a little check mark underneath 20. Now, around at negative 1, well, there it really doesn't do anything because it just bounces off. And then for our next point here, well, that's at about negative 0.3, but you might notice that this isn't actually a minimum value because we are increasing into the point and then decreasing after. So while negative 20, I'll go ahead and put is a minimum, at x is equal to negative 0.3, we actually have a maximum. And now over here at x is equal to 0, they didn't list that one in the problem, but let's just go ahead and see what that is. So x is equal to 0 is that point right there. And so it is decreasing into the point and then increasing afterwards, which means this will be a minimum. And then over here at about 2.5, which is our last value that we had, we can see that we are decreasing into the point. So decreasing into it and then increasing afterwards. And I know it's kind of hard to see, but that point should kind of look like that for the slope. So we're slightly to the left and then we go slightly to the right. Oh, I'm sorry. Actually, that point there should be like this, because from 0 we're going to a positive, or after 0 we're going to a positive value, and since we have no intercepts or anything, it should be like that. So it's a good idea to actually draw those so you can actually read them a little bit better, or get a nice enough graph so you don't make the same mistake I wanted to do at first. So that actually says we're increasing into the point and then decreasing afterwards, which would mean at this point we have a max. So actually 2 of these, even though we estimated them to be minimums, they're actually supposed to be local maximums of our function. Now that we've done that, we can go ahead and use the second derivative to find our possible points of inflection and all of that, and intervals of concavity. Now, what I went ahead and did was found the second derivative using our CAS software, and this first graph is just an overarching graph of it. And the only information that we really will need to look at is to the left of our vertical asymptote at x is equal to 2. So I went ahead and blew that information up. And this is what I ended up getting for our interval. And I kind of went out kind of far for the x-axis, and it didn't really look like it had anything else. So these, I would say, are all of our x-intercepts. So let's go ahead and find our intervals of concavity now. And let me go ahead and get rid of this arrow just to give us a little bit of space. So this function will be concave up. So I'm going to start from the left. So I'll start on this one here so we can start looking at everything. So when f double prime of x is strictly larger than 0. So that's going to be from negative infinity to about negative 4.978 union with, and then negative 1 to 0.543 union with, and then negative 0.108 until our first intercept, or vertical asymptote, at x is equal to 2. And then the rest of our domain should also be greater than 2. So it would be 2 to 4, union 4 to infinity. So then that tells us the rest of our interval should be where f double prime is less than 0, which is going to be negative 4.978 to negative 1 union with 0.543 to negative 0.108. And so remember, f double prime less than 0 means concave down. And when f double prime is strictly greater than 0, this is concave